Hi there, Mr. Sutton here, bringing you the AB Calculus 6-6 classwork solutions on motion and position. For this calculator-based problem, we have a particle moving on the x-axis so that its acceleration is given by this crazy function over here. If the velocity of the particle is 2 at time 1, we want the velocity of the particle at time 2. So this is essentially a fundamental theorem of calculus kind of problem, FTC. To get the, this is v of t, v of 2 we're looking for here. To get v of 2, we're going to use v of 1, which is just 2, plus the integral from 1 to 2 of this a of t function, because the acceleration is the derivative of velocity. So let's plug this in our calculator now. So I have my function here entered as y1, and then quitting out of there, I'm going to do 2 plus integral from, we said 1 to 2, and that's going to be, let me do alpha trace y1 dx. Plug in all that in, we end up with 3.346. So that's going to be choice E. For this problem, we have a particle moving on the x-axis with a velocity of 4 minus 6t squared. If we have a particle at a position 7 at time 1, we want position at time 2. So this is an FTC kind of problem, but it's no calculator. So we're actually kind of have to do this integral out. But I can start by saying v of, let's see, well actually we want position. So x of 2 is going to equal x of 1, which is 7, plus the integral from 1 to 2 of x prime of t, or v of t dt. So now I have to take the antiderivative of this expression here. That's going to be 4t minus, let's see, if this bumps up to a 3, we have 2t cubed. And we're doing that from 1 to 2. So that's 7 plus all this stuff with 2 plugged in, minus all this stuff with 1 plugged in. We're going to have to crunch the numbers on this one because it's multiple choice. So for this first brackets here, we've got 8 minus 8. Actually, no, 8 minus 16, so that's negative 8, so 7 minus 8. And over here, this is just 4 minus 2, which is 2, so we've got minus 2. So this is essentially 7 minus 10, or negative 3, which is choice C. On this problem, we have a particle moving on the x-axis, and they're giving us the acceleration function. They're also giving us the position of the particle, which is 10, when t equals 0. And they give us another position when t equals 1. Based off this, they want the velocity of the particle at time 0. So this is kind of a unique problem. Usually we start with acceleration and we have to figure out the position, but they're giving us different positions. We need to figure out the velocity based off of all this. So it kind of appears we don't quite have enough information to do everything we want, because they're not telling us, for example, an initial value for our velocity. But we're just going to have to work with it and do the best we can. So I'm going to start by trying to get at least a hint of what the velocity function should be by taking the antiderivative of my acceleration function. So I'm going to do a little diffie q magic here. Antiderivative of a of t is going to be v of t. And then this is really 15t to the 1/2. That bumps up to 3/2. Multiplying by 2/3 now, the reciprocal, we've got 10t to the 3/2. Plus c, and I'll call this c1 because I'm going to have a c2 later on here. I usually do end up with things like that with this acceleration to position kind of deal. Next, normally this is the point where I would take the value that they gave me for velocity, plug it in over here and plug in the t value and find c1, but they didn't tell us anything about the velocity. In fact, they want to know the velocity at time 0. So we actually have no choice but to keep going and hope that we can use these two positions they gave us to somehow get to the bottom of what this c1 value is. So going one more antiderivative of v, that's going to be x of t on this problem. And then this bumps up to a 5/2. Multiplying by 2/5, I've got 4t to the 5/2. Plus, this will be c1 times t, because c is a constant. And then I'll add another c2, just another constant, at the end of all this. All right, so I've got a whole lot of unknowns here. It's time to start filling in some of the gaps. They told me that if I plug in 0 for t, my x value comes out as 10. So I'm going to write 10 equals all of this stuff with 0 plugged in for t. Now the convenient thing here is that actually zeroes out this C1 term that we didn't really know what it was anyway. So that just leaves us with C2 equals 10. So I'm going to rewrite my position function now, x of t, with this 10 filled in. So I have 4t to the 5 halves plus c1t plus 10. And the good thing is they actually gave me another position now. Now that I've figured out what c2 was, I can plug in this other position to figure out c1. And then I can use that to go back and work with my velocity function. So plugging in 20 for x, that means we plugged in 1 for all of these t values over here. And crunching the numbers, this is just 4 plus 10 is 14. So we essentially have c1 plus 14 equals 20. Subtract the 14, we've got c1 equals 6. So now I can rewrite my velocity function as t times 10 to the 3 halves plus 6. And we wanted to know the velocity at time 0. So at this point, we just plug 0 in for t, and let's see what we get. So this is going to zero out that whole first term, leaving us with just 6 when all is said and done, so choice D. On this problem, we're given a table with velocity values for some particle moving along the x-axis, and we're told at time 0 the particle's at the origin, which could be the graph of our position from the time 0 to 4. All right, so just rating these graphs here, we have an output, or rather an input of t, and the y-axis here, ironically, is actually giving us the x values at time t for this particle. So keeping that in mind, let's try to use some process of elimination here. Now, we see that at time 0, the particle's at the origin. That means the output value ought to be 0. X of 0, 0 should be 0. Looking at our answer choices, choice B does not start at the origin here, so that can be eliminated. Same thing with choice D. Neither of these have an output value of 0 to start with, so right off the bat, they fail. Moving on, we see that our initial velocity, or at least the velocity at 0, is -1. So we're going down from the origin. Looking at answer choice A, that's going up from the origin, so we can eliminate that one. And that leaves us with C and E, which both went down initially from the origin. Now, between those two, I'm looking at my next velocity here. I have a velocity of 1 that's 2. The most important thing here is it's not 0. Because looking at these two answer choices, C has a velocity of not 0 at t equals 1. E, on the other hand, this looks to be 0 or pretty close to it. I mean, whatever this slope this is right here, it's definitely not 2. So E can be eliminated based off of that, leaving us with just answer choice C. On this problem, we're given the graph of the velocity of some particle that's moving along the x-axis between times 0 and 6, and we're given a whole bunch of other information. Most relevantly out of this whole passage is the fact that the areas between our velocity function and the t-axis here are going to be 8, 3, and 2, without respect to signage there. So some of these might be negative area when we need to use them. And we're also told at time 0 the particle is at x equals -2. Based off of this, we want to know how many times the particle has to go through x equals -8. Well, when we're talking about how many times or whether or not a function has to take on a certain value, we're generally talking about the intermediate value theorem. So to establish the preconditions of this before we start reasoning in that vein, I'm going to take a look again where they said we have a differentiable v function. Well, that implies that the x function itself must be continuous. If we have differentiability, we have continuity. So that means that I can now just try to sandwich this -8 between the various values of x at these different spots, and hopefully that'll tell me how many times we're going through -8. So I'm going to set up a table. I've got a t value and an x value, and there's 4 of these I really care about. At t equals 0, for example, they told us x equals -2. So we're kind of hoping that when we add our area in here, we're going to next get a value that's less than -8. So at t equals 3, to get that we have to do -2 minus this area of 8 here. That comes out to -10. -8, this x equals -8 that we're looking for, is definitely between -2 and -10. So that's at least once that we're passing through that value. But let's keep going. Now to get to t equals 5, and I'm picking 5 because that's the next t value where I've got the whole area bounded and figured out here. So at t equals 5, we have to do negative 10 plus this area they gave us of 3. So that comes out to negative 7. And then finally, let's go all the way to t equals 6, where we have to do negative 7 minus the area they gave us of 2. That gives us negative 9. So I see, looking at my values here, that the negative 8 I was looking for is between x of 0 and x of 3. It's also between x of 3 and x of 5, and x of 5 and x of 6. So that means that by the intermediate value theorem, we are guaranteed to pass through x equals negative 8 on the interval from 0 to 3, from 3 to 5, and from 5 to 6. And we're guaranteed to go through negative 8 at least once on each of these intervals. So overall, that means that at least 3 times we're going to be passing through x equals negative 8. For this calculator problem, we have a particle moving along the y-axis with a velocity given by this function here, and we're told at time 0 particles at y equals negative 1. So for our first part, we want to find the acceleration of our particle at time 2. To figure this out, if I want a of 2, I need to find v prime of 2, and I'm going to write out explicitly that these things equal each other. Next, I'm actually going to figure this out on the calculator. To make my life a little easier, before I do this problem and any others, I'm entering that velocity function they gave me in my y equals, so that way I can just keep using it and not have to do a whole lot of other work. Now, what I'm doing on this problem, I could actually figure out what my derivative looks like for this, but I don't really need to know that at this point. All I really need to do is take the derivative of v at a single t value, for which I don't need to actually show what I'm plugging it into, more than just showing it's v prime. So going to my calculator for this then, I'm going to do math 8 for derivative. We'll have a dx down here, alpha trace y1 for my input for my derivative, and we wanted that at an x value of 2, or a t value in this case. So that comes out to negative 0.133 if I take it to 3 decimals. For the next part of this problem, we want to know if the speed of the particle is increasing or decreasing at time 2 and give a reason. So for this, we have to compare the velocity and the acceleration. Acceleration we figured out was negative. The velocity, when I plug 2 in for this function, let's see what that comes out to on the calculator. So plugging that in, I get a value of negative 0.436, and that is negative. So since velocity and acceleration have the same sign at time 2, that means our particle speed is going to be increasing at that time. Since the velocity and acceleration agree on direction, we're actually speeding up. For this part of the problem, they want to know the times at which our particle reaches its highest point, and then justify that. So we're going to start by finding critical values for the velocity, because those turning around spots for the particle will most likely be the highest point. So let me graph this now. So going to graph this, I've already got this velocity function entered in my y equals. So I'm just going to go to zoom, and we'll just do zoom 4 to get something approaching a standard window here, but a little bit closer than the normal standard window. We see there is a crossing here at this value between 0 and 1. Let me do second trace and figure out what that crossing actually is. So we have 0, click a little bit to the left, a little bit to the right, enter one more time, and that comes out to about 0.443. So right there. Now, is that the only place where our particle is crossing the x-axis? We can't tell just by looking at this window, but if we do a little bit of analysis in our heads here, let's talk about the limit as x approaches infinity, or as t approaches infinity. Well, as that happens, you're taking the inverse tan of an infinitely large input. Now, inverse tan takes a slope and gives you back an angle for that slope. So you're basically asking, at what angle do I have an infinitely large slope? Well, that would be the angle 90 degrees, because as you get closer and closer to 90, you're closer and closer to straight up for your slope. So that would just be a constant. 1 minus a constant is not going to keep going all over the place. And as we do negative infinity, we just get the constant itself there. So that means when all is said and done, this is the only crossing that could possibly exist for this function. All right, so what does that mean? Well, if we had a closed interval, we could test this value along with the two endpoints in the original function if we could figure that out based off our velocity and the initial value here. And that would give us some candidates we could test. There's just one problem. They did not give us any kind of bounds other than t greater than or equal to 0. So we're going to have to just kind of work with that. So the way I'm going to justify this is using what I call the lonely extreme test. Since our velocity changes from positive to negative at 0.443, so that's saying basically we have a local max there, and there are no other critical values, this particle has to reach its highest point at that time. Just to think about the reasoning behind this, if you are having a positive velocity until you get here, that means your particle is increasing until you get here. So if it's been increasing this whole time, then nothing to the far left here can give you a higher value than you've got at this crossover spot. Now, by the same token, your velocity is negative after that spot, so that means it's decreasing forever after. So this has to be the absolute max for the whole graph. For this problem, we want the position of the particle at time 2, so this initial condition's finally going to come in handy, and then we want to know if the particle's moving toward the origin or away from it at that time. Well, we're going to need the position to figure out this second question anyway, so let's go ahead and find it. So that's going to be your y value at time 0, y equals -1, so this is what y2 all equals, -1, plus the integral from 0 to 2 of v of t dt, where v is really just y prime. All right, let's plug all this in. Entering all of that on my calculator with v of t stored as y1, that all comes out to about -1.361. All right, so we have a y of 2 that's negative. And from part B of this problem, we saw that v of 2 was also negative. You can check back there to see just how negative, but it is negative. Well, since we have a particle that is starting to the let's see here, if the y value is negative, we're starting below the x-axis, and according to this velocity, we're decreasing. Given those two conditions, that means we're moving away from the origin at time 2.